Okay, so it looks like we are recording now. Very good. So hi everyone. So welcome back. So this is Advanced Calculus Lecture 5. Now we are going to continue cross products today. So hopefully we are going to be done today. So let's see how it goes. So one of the things that we did not discuss is some of the other properties of cross products. So, so recall for vectors like A and B in R3, right? So given two vectors A and B in R3, we define a cross products. So basically, we defined it in two ways, right? You remember we had a geometric way of defining it, and we also had a purely algebraic way, remember? And the beauty of the subject is that this geometric definition perfectly matches with the algebraic definition. Each of them captures just some aspect of cross products. So I don't need to recall the definitions. So I mean, e.g., in algebraic kind of form, this A cross B was defined by I, J, K, A1, A2, A3, B1, B2, B3, right? So this was defined like that. And then we check some of the properties of this cross products. So one of the things that maybe I mentioned, but I'm not sure I did. So this is the distributive property of the cross product. So one of them was like that. Distributive property, let me just. So can you tell me from kind of what we had before, maybe discussions, what distributive property in this case would mean of cross product? Means that adding in A, for example, the first component, distributes over cross products. So in other words, it just means this, A1 plus A2 crossing with B is equal to A1 cross B plus A2 cross B. It can also be called linearity in this case, but we call it distributive. I mean, I think the book calls it distributive. And same with A cross B1 plus B2 is equal to A cross B1 plus A cross B2. So we also had some other properties, but some of the things that you might think they are okay, they go through, they won't. For example, one of the things that fails is what? Can you tell me one sort of property of manipulation of numbers that won't go through in this case? Operations that look natural to be true, but it's not true in this case? Can you tell me? Yes.
A cross B is not equal to B cross A.
Yes, indeed. It's not commutative, as was mentioned. Right. It's not commutative, so not commutative. So A cross B. But can you tell me what is its value in terms of negative B cross A? Exactly. It's negative B cross A. And A cross A, as a result of this, is equal to 0. We showed all these things last time. Can you tell me one more property of numbers, operations with numbers, that does not hold in this case? Okay, so yes.
It's non-associative.
It's not associative. So you're saying that A cross B cross C need not be equal to A cross B, cross C. So this means not associative. Okay, but why it's not associative? Let me just answer some questions. Okay, so not symmetric, yes. Associativity, yes. I had good answers. Very good, thank you. On overview side. Okay, yeah, I got your points. Okay, so very good. I got your points now. Okay. So let me just close this so that I know when there's a chat, I know exactly what's going on. Okay, very good. So, can you then, you have to give me an example. If you believe this is not true in general, you have to give me an example. Can you give me an example that this is not true? So you have to give me 3 vectors, A, B, and C, such that if I multiply in this order, I get a different vector if I multiply in this order. Well, just why not using the basic coordinate vectors, I, J, K, right? We can just, but then how we are going to do it? For example, let's try I cross J cross K. Is it equal to, so I put question mark over, is it equal to I cross J plus K? Let's see, is this equal to that or is not equal to that? So let's compute. I cross, what is J cross K? Okay, to do J cross K, we have to remember the definition, right? This was I, J, this is K, right? So what is J cross K?
Yes. Negative I.
Is it negative I or is it I? Because if I put my right hand, I go from J to K, my right hand seems to be pointing in the direction of I, right? So this is going to be I. What is I cross I? 0. 0, by what we discussed. So this is equal to 0. Now, what about the right-hand side? What is I cross J? Is K, exactly. And so K cross K is 0 again. So in this case, they came out to be the same, actually. So we have to do a little bit of thinking, maybe constructing examples such that, okay, I've got 3 comments now. Not symmetric, okay, yeah, good, yeah, I've got, use the unit vectors I, but I just used it, so it didn't work so easily. Maybe you mean something else. I think I know what you mean. You have the right idea, I know what. So what should we use instead? As you're thinking, let me just erase this one. Okay. Answers? Yes.
Could you use I, J?
Mm-hmm. This looks more promising indeed. Let's use I cross J. That's what you're suggesting, right? So, and is it equal to, by any chance, I cross J? Okay, so what is left-hand side? So left-hand side is I cross, we just discovered what is J cross K. Oh, no, I cross J is K, right? So this is I cross, this is K. And what is I cross K? Can you tell me what is I cross K now? It's negative J, yeah, indeed. Because if you do K cross I, your thumb would be in the direction of J. But now we are doing the opposite, so that's going to be negative J. So that's all in the left-hand side. What about right-hand side? I cross I is 0, right? So this is 0 cross J, of course, is 0. So indeed, you're absolutely right. I mean, The left-hand side does not match the right. So in fact, this was kind of strange that we took these three orthogonal vectors, they matched. Usually, if you take three generic vectors randomly, it doesn't match. So this was kind of accidental. That at first they were equal, but in the generic more or less case, I think they shouldn't be equal. So this is a property of non-associativity. So we conclude that A cross B is not associative. That's important. That's good. Any comments or questions? No. All right, so now we discussed that. So I believe one of the things, yeah, we had one application of dot product into to physics. You remember what application I mentioned to physics of dot product?
Work.
Work, yeah. So we discussed the idea of work as a kind of nice application of dot product in physics. Now we are going to mention an application of dot product, yeah, work, very good. A cross product in physics. Yeah, answer? Yeah, exactly, it's torque. So torque, for torque, you can think of as rotation, the amount of rotation, or yeah, kind of rotation as cross product. So when we have this say one axis like R here, there is some mass or whatever, is hinging on this point O. So this kind of bar is hinging on O, is fixed in space or whatever, in a plane, for example, at O, and the vector is R, and you're applying a force like here, like that. I mean, it could be in any direction that you wish, right? It doesn't matter. So, and then the torque tau of force F on this bar is given by R cross F. So that's kind of the amount of rotation that this force imparts on this handle R, basically. So that's kind of amount of, the amount means here of rotation that F imparts on the handle R. So for example, if F is along R, right? E.g., if F is parallel to R, the torque is 0, right? Then torque is equal to 0. And that's intuitively quite clear because if you are applying a force to this only along R, you're not imparting any kind of rotational movement to R by that. And the maximum rotation that you can do is, of course, is going to be orthogonal to this, right? So the maximum rotation is going to be orthogonal. So if you go like that, this is so on and so forth. Okay, so this torque is a concept that is extremely useful when we apply kind of cross products to ideas of physics. Do you remember any of the other concepts that you might have seen in your physics courses that use the cross product by any chance? Or there was an answer, work? No, it's torque. Sorry. Torque and work kind of rhyme, but they're not the same. Right. Thank you for answering, though. That's great. Okay, so any other concept from physics that involves cross product? Yes.
Magnetic force.
Magnetic force, yes, that's this B indeed. Yes. What is magnetic force?
QVB sine theta. So it would be
Is a cross product of.
QV cross B.
Yes, exactly. Is a cross product of magnetic field by velocity. That's Lorentz force law, right? That's velocity. But now I can give you something which is along those lines, but it's kind of different. That's angular momentum, right? What is angular momentum? As a second concept. So angular momentum L is, you remember the angular momentum? Yes. R cross P, which is mv. Remember? Is R cross mv. But this mv is momentum P. When you cross it, you get angular momentum. So m is mass, v is velocity, and R is position vector. So the situation is that a particle, for example, is moving in space. At some point, its position is R and its velocity is V, right? And you want to know the angular momentum. Well, cross R with V, these are two vectors, and then you have to multiply by it. You see, these two things look similar, but don't confuse them with each other. Torque is very different compared to angular momentum. Okay, both of them contains this R, but the other one is your force that you are, but here is momentum. So they are very different concepts, but they look similar. Okay. So that's one more thing, and I think we are done basically with this sort of applications to concepts. Now we can just go and do, we are done with cross products essentially now. So we're going to start talking about equations of lines and planes using dot product and cross product again. So let me just write now. So good. Any questions or comments? Okay. So equations of lines and planes. I believe this is section 2.5 in your book. So, how can you fix, first of all, let's look at line. Fix a line in space. You can fix a line in space by giving me one point on the line, like R0, right? This is a point on the line. And also giving me the direction of the one vector that lies on the line. If you give me this direction, right, V, for example, then you have completely specified the line. So that's because what is a point on the line? Well, a point on the line is going to be R0 plus some multiple of V, because you can be anywhere on the line, right? So you can be here, you can be here, you can go here. Okay? So in general, if you are like at distance t or something from this R0, this is going to be your vector t. Right? So, and then this is your coordinate, this is the thing, right? So your R that is going to be R0 plus TV. So very good. So all of a sudden we discovered that if you know one vector which is on the line and the direction of the line, any other point in the line can be specified by this equation. So let me now write it down. Maybe R0 is any point vector on the line, and V is direction of the line. Okay. So the idea is that we have to know these two parts of these two pieces of data, of course. I mean, because you have to tell me what line is. I mean, where is this line? I mean, is this one, that one? So R equal to R0 plus TV. And T is anything, it's just a parameter. This is called a parameter. As you change T, you're moving on the line from kind of minus infinity on the line to plus infinity on the line. Although, I mean, technically we don't have infinity. I mean, we have far away points on the line. So this is the equation. This is called the vector equation of the line. So this is one is vector equation of A, which is this one. Now let me ask you a question. How many numbers you have to give to your computer in order that your computer understands where your line is? Because you have to punch in some numbers, right? You have to, you want to tell a robot to go and walk on this line in the universe. How many pieces of numbers you have to tell to me or to your robot or to your computer so that he or she knows where the line is, how to draw the line? How many pieces of number is needed?
In 3D space?
Yes, exactly. Yes, yes.
I was going to say a starting point and a slope.
But in 3D, just think about it in 3D. So the starting point is R0, exactly. But is that enough? No. You need also this direction V, right? You need the direction V. So how many numbers is contained in R0? 3. And how many numbers is contained in V? Again, 3. So what you need is 6 numbers. So a line is completely specified by 6 numbers. Give me 6 numbers. So this is a bit of. I got answers 4. I think you were thinking about 2-dimensional space. Yeah, in 2-dimensional space, yeah, indeed, this is correct. Yes, very good. But yeah, but in 3-dimensional space, you need 6, right? You see that because you saw 4, right? Very good. Okay, so that's what we have. All right, so now, but we can write this equation now in a different form. This is the vector form. So now let R0 equal to those 3 numbers that I mentioned, x0, y0, z0, and let V be equal to ABC. And here also you see there are 6 numbers, x0, y0, z0, a, b, c. So we have 6 numbers. So fit these things, and then we are going to write this vector equation in x, y, z, right? So and R equal to x, y, z. Then this equation star tells us that, okay, so we have got x, y, z is equal to x0, y0, z0 plus t times abc. Okay, you can just spell this out. You get x, y, z equal to x0 plus ta, y0 plus tb, z0 plus tc. So you get the equation that x equal to x0 plus ta, y equal to y0 plus tb, Z is equal to Z0 plus TC. So we found a completely equivalent form, but looks different, but it's completely equivalent for the equation of the line. This is called the, I believe it's called the parametric form of the equation. Right. So this is parametric form. But notice that this is completely equivalent to that. I mean, okay, this is a bit cooler to write it like this, right? Because it's just like one line. So we are given the equation of the line. But of course, a lot of things are hidden here, right? So when you start unpacking things, you get these three equations. Again, T is the same. Is a parameter, right? So T belongs to R is a parameter. Okay. So this T is not fixed. T is changing from minus infinity to plus. It moves, and then you get all different points for different values of T, right? So now there are two comments in the chat. Okay. Why we don't count the parameter T as a number? Oh yes, that's a good question. Only your line will become a line segment. Only your line will become. Yeah, you see, if you no, this is not this T is not. What is the question actually? Why we don't count the number T as a number? Oh yeah, the T, because T changes, it's kind of customary to call it a parameter. Parameter is something that you can change. It's not fixed, right? This X, Y, Z, I mean, it's changing, but X, Y, 0, Z, 0 is fixed, ABC is fixed. So that's parameter is something that is allowed to change. When you're allowed to change something, it's called a parameter. Right? So now you can now write it yet in a third form. Equation of a line in a third form. Let me write it. I believe this is called the symmetric equations. So this is the equation of a line. In symmetric form. So what you do, you just subtract x by x0, y by y0, z by z0, and divide by ABC. So from here, so this is like double star. Right? So this double star tells me that x minus x0 over A is equal to y minus y0 over B is equal to z minus z0 over C. And of course, they are all equal to T. But in this form, we don't emphasize T, we just take this. Of course, this is allowed only if A, B, C are, all of them are non-zero, right? Otherwise, because we cannot divide by 0, so this won't be allowed. So provided that A, B, C is different from C. Right? So this is called the symmetric equation of the line. So we have discussed three types of equations for the line: the vector equation, parametric equation, and symmetric equation. So vector equation. Parametric equation. And symmetric equation. So these are all the same, but they are kind of, they look different, and there are some advantages working with one instead of the other, things like that. But essentially, question? No? Okay, so now let me give an example. If there are no questions, let me give some sort of example here. Okay, so how is, am I in the limits? Yes. So here's an example. Find the symmetric equation of line passing through points P equal to 1, 2, 3, Q equal to -1, -1, 0. Right. So we are given 2 points, so solution. We are given 2 points. P is here, Q is here. And this is, of course, 2 points in space. If they are not the same point, they define uniquely a line, right? It kind of stands to reason to believe that what I'm saying is correct. 2 points in space, there's a unique line connecting, I mean, a straight line connecting the two, right? So this is kind of, but now we want to find the symmetric equation of this line using this formulation of symmetric equation. So the question of obviously is what is x0, y0, z0, and what is ABC. That's what we need. Do you want to take a minute, maybe try your hand with this problem? Also at home, do you want to try this maybe? Okay, yes. Okay, the line segment I will answer later. Yeah, very good. In other words, the question is, for example, what is R0? What is V? Oh, I already had an answer here. Okay, so well, I don't know. I hope it's okay. I think you're right, but I can't confirm. I have to do it myself. It looks you know what you're doing. Yeah. Okay, so several answers. Very good. So now, so how did you do it? Did you try? This is easy, right? I mean, that's okay. So how would you do that? Well, you can take either of P or Q as your R0. Let's take R0 equal to, so solution, let R0 equal to P. So then I have the components of R0, which is 1, 2, 3. Now the question is, what is V? But V is just the difference of these two vectors, right? It's Q minus P, right? So it's just Q minus P. I mean, I write it like that now, but so this is what I mean, really. So Q is -1, -1, 0, minus. P is 1 to 3. So we are going to get -1, -1 is -2. -1, -2 is -3. And this is -3. I hope I didn't make any mistakes here. It's okay. This is V. Okay, so now I can write the equation in the form x minus x0. So x minus x0. So this is like x0, y0, z0. So this is like x minus 1 over, now this is ABC over -2 equal to x minus 2 over -3 equal to x minus 3, right? Oh, this is y, I'm sorry. This is z minus 3 divided by negative 3. Now, you might have got different answers than this, and you may very well be correct as well. There is not a unique form of this, right? If you have this equal to that, you can multiply everything by minus 1, for example, everything by 2. Still, you have the equality, right? So, there is not a unique symmetric form. Actually, the equation of line is not unique. Can you tell me why the equation of a line is not unique? Yes. You see, what if, for example, what if I chose here, instead of q minus p, what if I did p minus q? Would it be wrong? Yes.
You would just be switching the direction.
You're just changing the direction of the vector. It doesn't matter. The line is going to be the same because the line just has to remain on the same vector. The line doesn't have a direction. The line is just a line. It doesn't have a direction. So that would be, yeah, change of direction, exactly. So, so that didn't change anything. Would it be different if I chose, instead of q, some point in between? No. Of course, you have to make sure the point you choose is really in between. It's not somewhere else. That would be really different. Right? So these are all small points that we want to. Could you have used Q for R0? Yes, we could have used Q for R0 for sure, or change direction. Exactly, exactly. Yeah, okay, very good. Okay, so that's good. Now there is a really cool application of cross product to finding distance between a point and a line. This is completely should convince you that cross product is the superior language compared to elementary methods. So this is distance from a point to a line. So imagine a line is given like that. There is point R0 and there is this vector V. Right? So these are the two parameters of the line. I mean, 6 numbers, R0 and V. A point on the line and a direction vector. And you have a point P outside. Right? Maybe a point P outside. And what you want is the distance between P and V. So that's the question. Distance from P, I mean not P, from this line. So this line is L, from P to line L. So what is the distance? I mean, okay, so this is a line in the space and that's a point outside. What's the distance between this point and line? Well, the idea is this. You are looking at a point such that if you draw this line, right, this is going to be an orthogonal point. Right? So you have to find a point on the line, like Q, such that this vector, first of all, Q is on the line, and second of all, this vector has smallest length. And we know that by geometric intuition that the smallest length happens when PQ is orthogonal to M. Right? So geometry tells us that smallest length, or smallest distance, which we are going to call the distance actually, because the idea of distance at first is a bit ambiguous, right? You have P and you have all these different points, right? So we're going to measure. So which one we take for distance? We take the point that's closest, right? Point on L that's closest to P. Okay, we do that. So smallest distance from P to a point Q on L is when PQ is orthogonal to V. So how we are going to find this distance now? So let's call this distance, for example, D. How we can find the distance? Well, there is one way, which is a kind of sure bet. You can take just a parameter T, write a general point here, and find a formula from P to that arbitrary point, and then minimize. So this would be a minimization problem. Then you have to use calculus to solve that problem. So that's a bit of a lengthy process if you want to do it that way. What would be a kind of maybe a better method to solve this? Just to be maybe I just use maybe to be consistent in my notes. I just use n because I'm going to refer to my notes later. And this is the point. Okay, so how we are going to find this distance from M to the line without using calculus, without using derivatives, by just using cross products. Any ideas? So what we get if we cross NP by V, for example? NP okay, so here I have actually that's better. So this is going to be yes. So here I have to correct my notation from M to a point, say Q. So P is the point. Yeah, I'm just sorry. I'm just changing my notation to be consistent with my notes. So smallest distance from M to a point, say Q on line is this has to be so. Yes, MQ has to be orthogonal to B, but that's not what we are paying attention. Now, what do I get if I cross NP by V? For example, right? What do I get if I cross NP by V? And what is its norm? Norm of NP by V. Yeah. Yes.
Is it the area of that?
Exactly. It's the area of the parallelogram that's formed by this and that. So in particular, is twice of the area of this area, right? So that's what we remember now. MP cross V is equal to twice area of this delta. So delta is this triangle that I draw here, right? Yeah. At first we had the area of the parallelogram, but the area of parallelogram is twice the area of the triangle, right? You agree, right? Yeah. So that's what it is. Good. So this we know. We have the coordinates of M, we have the coordinates of P, and this is the. Now, on the other hand, how can I compute the area by using D and this length of this vector V? You can compute the area in a different way, right? You can compute the area, so let me write it here. On the other hand, area of delta is equal to half of what? Half of what? Half of D times this vector which I call V. So this is my P equal to R0 in my notation. So this is this vector V. You agree? Is equal to half of D length of V. So we have two ways of computing the area now. One method is this, which says that area of this triangle is half of that quantity. A second method says that, so if you compare these two formulas, so A and B, comparing A and B, you do get indeed that 1/2 length of the vector MP cross V is equal to, so this is the vector MP, sorry, is equal to 1/2 the length of your vector V. And D is what we wanted to know. So D comes out, so I just write it here, then I think I'm in the frame still. D, you get the following formula. This 1/2 cancel. You get length of MP plus V divided by length of. Now, you see that this is really cool, right? Because this was not easy. This is indeed it's not easy to obtain it by sort of direct method. Because the direct method would be, I invite you, maybe if you have time at home, check the direct method. Just write down in parametric form equation of the line and try to minimize, and then you'll see that V cross M minus R0. Yeah, yes, this is essentially correct what you have there, but because I changed my notation, so I prefer to use this notation, but you're right. Another question is, could you not use projections? We are in a way using projections, but we are doing something else now. What kind of idea we used? What kind of idea we used? We used several ideas, right? One idea was that the area, the magnitude of the cross product is really the area of the parallelogram formed by those two vectors, which is twice the area of any of those triangles, right? That was one idea. But we used another idea which was very, very mischievous, actually. We used very, very slick idea here. I mentioned this last time, actually. What second idea we used? We computed the area of the triangle in two different ways, right? And we said that because the area is the same, so they have to be the same number. But we used something totally amazing. What did we use? We said that this times that is equal to this cross that in length, essentially. That's not obvious at all. That's not obvious at all. I mentioned this last time. You remember what we discussed last time? We discussed that, for example, I mean, if you have a triangle, I mean, in the case of triangle, but actually we had in the case of parallel part, so which is even more involved than this. But let's look at this case. In the case of triangles, I said that this multiplied by that is equal to this multiplied by that. I'm assuming this is 90 degrees, and it's also equal to this kind of thing multiplied. Well, in this case, it's the same. But if these are like not, I mean, if this is the kind of 90 degree, for example, this is bad form. You see, this multiplied by that is equal to this multiplied by that is equal to this multiplied. Assuming that these are, what are those perpendicular lines called? In geometry, if I drop a line orthogonal to this, what this line is called?
I know there's a word for it, but
I know there's a word for it. Do you remember? Anyone from the audience at home remembers what's the word for that line? You draw from vertex of a triangle to the opposite side. Height? Is it height? Height is the length of it. Yeah, it is length. It's called height of the triangle. Well, triangle has three heights actually, right? Because of three. What's it called? Well, I don't remember now, so you're excused. So.
Yeah.
Bisector? Bisector cuts the angle in half. That's, and there is normal. Yeah, normal sounds right. Normal sounds right. Yeah, normal. And the one that lands on the middle of the opposite page, what's it called?
that's a median.
That's median.
It's called a median.
This one is not median.
That's in geometry, a median of a triangle is a line segment joining a vertex to the midpoint of the opposite
To the
side.
midpoint. That's my last question.
Oh, yeah.
She answered also. That was the median. But what about the normal line?
Okay, altitude.
Altitude? Oh, yes. But altitude, I thought that you were going up on mountains. You said, I'm in high altitude.
So height was close.
Height is close. No, absolutely. No, absolutely. Height is close. Yeah. Altitude. Okay, guys, it was altitude. Thank you very much. So we just stop here. We go off camera now. How do I pause? Pause recording.